Hey everybody. Today we're going to continue with our discussion on solutions and how to measure the concentration of certain solutions. So in the prior videos, we talked about percent concentration, which is a really important calculation for many areas. But chemists love the calculation and measuring concentration using molarity. The reason why they love molarity is because we tend to think of things in terms of the chemist's dozen, Avogadro's number, the mole. So molarity is basically the same concept, however. It is part over whole. It's basically a certain amount of stuff that we dissolve. So an amount of solute, that's my part, over the solution, that's my whole. Now for molarity, the units are moles of solute per liter of solution. And we'll see when we do our stoichiometry that that's very useful because we can convert to moles rather easily. Molarity a lot of times is referred to as a molar solution. So one example is if you see a 3 molar hydrochloric acid solution, what that basically means is I have 3 moles of hydrochloric acid per liter of that solution. So it basically is a concentration. It's how much solute is dissolved in the entire solution, part over whole. There is no times 100 here because it is not a percent concentration. So how can you make a 1 molar? A lot of times chemists get a little lazy. Instead of saying 1 molarity, they say 1 molar sodium chloride solution. Well, to get a 1 molar, another way of writing this is 1 big M. You basically need 1 mole per 1 liter. So if I want 1 mole of sodium chloride, how can I get that? It's pretty easy. I use the periodic table and I know that the molar mass for sodium chloride is 58.5 grams. I can take a volumetric flask and put 58.5 grams of sodium chloride, which again is the solute, into the volumetric flask. Then I can fill the volumetric flask partially, mix it well, dissolve that solute, and then what I like to call is bring it up to volume to where the meniscus reads 1 liter. If I do that, if I bring it up to volume to the 1 liter mark, then I have a total of 1 liter. The 58.5 grams is 1 mole of sodium chloride, and this would represent 1 mole of sodium chloride per liter of solution, or a 1 molar sodium chloride solution. So, calculating molarity, how do we do that? You typically think of molarity as moles per liter. So in this calculation, what is the molarity of a 0.500 liter sodium hydroxide solution if 6 grams of sodium hydroxide was dissolved in it? So 6 grams is my solute, the lesser amount. And they tell me it's a sodium hydroxide solution, so the sodium hydroxide is the solute. So I have my volume measurement in terms of liters. That's great. I could plug that into the denominator and figure that and plug that straight in. The thing that I need to convert right now is I need to convert my grams of sodium hydroxide into moles. And how do we do that? Like we've been doing all along, we use molar mass. I look at the periodic table and I see that there are 40 grams of sodium hydroxide. Again, where am I getting these numbers? Sodium's roughly 23, oxygen's roughly 16, hydrogen's roughly 1. That adds up to 40 grams per mole of sodium hydroxide. Convert the 6 grams of sodium hydroxides to mole using molar mass. I see that the units of grams of sodium hydroxide canceled, leaving me with moles, and I get 0.150 moles of sodium hydroxide. Now I can plug that into my numerator and plug the liters in my denominator to get the molarity of this solution. And I would actually see that the final answer is 0.300 molar sodium hydroxide solution. So that's one way to solve it. Some people think this is a little clunky. Why is it clunky? You first solve for moles, then you take the moles, you put it in a ratio, and then you divide it by the liters, and you get your final answer. A way you can do this that's a little bit cleaner and less clunkier is, I know I want moles per liter. This is a ratio, okay? If I want to end with the ratio, I can start with a ratio in my calculations. So what do I mean? I could have written 6 grams of sodium hydroxide per 0.500 liters. And now I see that I already have the unit of liter. The only unit I need to change is my grams to moles. And how can I do that? Just like I did above. I can say that there's 40 grams of sodium hydroxide per 1 mole of sodium hydroxide. And then my unit of grams of sodium hydroxide would cancel, and I'd be left with moles per liter. And I would get that value of the 0.30 moles of sodium hydroxide per liter. And you can do that on your calculator. What you have to realize, though, as we talked with ionic compounds, strong acids, and strong bases, they completely dissociate. And when they dissociate, you actually have a concentration of individual ions. So we have to account for the number of ions based on the ratio in the chemical formula. So if I had magnesium chloride, and let's say I had a 1 molar solution of this, in actuality, this dissociates and separates into a magnesium ion and 2 chloride ions. And I'll put aqueous just to show that they're in water and they've dissociated. So what that means is, if I started with a 1 molar magnesium chloride solution, I'll end up having a 1 molar magnesium ion solution. That would be the concentration, but I would have a 2 molar chloride ion concentration because of this subscript and the mole ratio in the formula. So can we determine it for sodium phosphate? So I look at my mole ratios in the chemical formula. If I have a 1.50 molar sodium phosphate concentration, when I throw this in solution, there's actually 3 moles of sodium per sodium phosphate. So I just take the 1.5 molar concentration, multiply that by 3, and this would actually be my concentration of sodium ions. The phosphate is a 1-to-1, so my concentration of phosphate ions would still be the 1.50. So how can we use molarity as a conversion factor? And really, you have to think of molarity as a conversion factor as opposed to a formula. So again, molarity is a ratio, moles per liter. Now, if you want to be more specific, moles of solute, the thing that you dissolve, per liter of solution, the entire whole. So if I had a 0.500 molar sodium chloride solution, I have 2 conversion factors. Either the moles can be on top and liters in the bottom, or I can flip this to cancel out units in my calculations. So how many grams of potassium chloride are needed to prepare 125 mils of a 0.72 molar potassium chloride solution? So What do I want? I want grams of potassium chloride. What am I given? Well, this is where students don't like solution chemistry. They see two things. They see 125 mils and they see the 0.720 molar potassium chloride. What I tell students, whenever you see this M, it is a conversion factor. You should think in your head and rewrite it as 0.720 moles of potassium chloride per 1 liter. And if I do this, then I can look at this problem and say, well, what I want at the end is not a ratio. It's not a conversion factor. So if I don't end in a ratio, I shouldn't start with the ratio. And if I shouldn't start with the ratio, then even though there's two numbers here, it's a lot easier to see that I should start with the 125 mils. Now, why is that useful? I can convert the mils to liters using the metric system, and we know there's 1,000 mils in 1 liter. And then from liters, I can go to moles very easily using my molarity. So I can go to moles. And then like we've been doing all along, I can go from moles to grams very simplistically by using molar mass. So what's my calculation? Basically, the 125 mils can be converted to liter because there's 1,000 mils in 1 liter. So dividing by 1,000, I just take this decimal and move it over 1, 2, 3. That's how I got that. Then I multiply my liters by the molarity. This is the big M. Again, big M, molarity, is this ratio. 0.720 moles of potassium chloride per liter. My liters cancel, I'm left with moles. How do I go from moles to grams? What we've been using all along, molar mass. I look to the periodic table and I look at the masses. And I see that potassium chloride has a molar mass of 74.6 grams. So the moles cancel. I'm left with 74.6 grams of potassium chloride per mole. And I calculate this out and I get 6.71 grams of potassium chloride. So that was a quick little demo on calculations using molarity. We'll have the next video showing how we'll use molarity for solution stoichiometry. I hope this made sense, and I'll see you at the next video.